Hello, everybody. Welcome to this Google Plus Hangout. I'm Karen Fox with the Office of Communications at NASA Goddard. And for the next hour, we're going to be discussing the recent discovery of the third radiation belt surrounding Earth. The radiation belts are officially known as the Van Allen belts, and they were the first discovery of the space age in 1958. In August of 2012, NASA launched two spacecraft called the Van Allen probes to examine the belts in the best detail that we've ever seen. And within days of launch, they had gathered information that really could be rewriting textbooks. Instead of the expected two belts, they watched a third belt form and persist for a full month. The discovery was published in Science magazine yesterday, and today we have 5 people to talk about it. We have David Sybeck, who is the project scientist for the Van Allen probes, Sri Kanikal, who is the deputy project scientist and one of the authors on the paper. Another author on the paper is here with us, Sasha Ukorski of the Johns Hopkins Applied Physics Lab. Alex Young is with us. He's a scientist at NASA Goddard who will speak about how the radiation belts are part of a larger space weather system. And finally, we have Washington Post reporter Brian Vastag, who covers science and space weather for the paper. Brian will be helping to facilitate the conversation today, so I'm going to turn it over to him in just a moment. Later on in the conversation, we will be answering your questions. You may send them in via the Google Hangout or via the Twitter hashtag Van Allen. That is VANALLEN. And with that, let's go to Brian.
Thanks, Karen. Happy to be here with everybody today. I'm excited to do this. I wrote a story that was in today's Washington Post about this discovery. It caught my attention because, as you said, we've known about these radiation belts since 1958, I guess, and yet it seems like they're still kind of mysterious, and we're learning all kinds of new things. So I'm hoping that, David, we can start with you, and you can just give us some background on the Van Allen radiation belts, why they're important, and kind of what they are.
Okay, thank you, Brian. As you mentioned, we've known that the Van Allen radiation belts existed only since the late 1950s, when Dr. James Van Allen launched a series of rockets up into the Earth's upper atmosphere. The surprising discovery he made was that space is radioactive. Those early rockets carried Geiger counters capable of measuring radiation in space. As time went on, we've realized they're quite extensive. The Van Allen radiation belts cover several Earth radii from Earth, and we've always thought, until now, that there were 2 of them. One close to Earth, about several hundred miles above the Earth's surface, and a second one further out, tens of thousands of miles above the Earth's surface. They pose a hazard to our spacecraft, and they pose a hazard to our astronauts, because radiation in space can cause cancer, prolonged exposure, and radiation in space can disrupt electronic circuits on spacecraft, can cause charging up and discharging on the spacecraft. They can simply ruin the spacecraft that we rely on. What do we rely on them? Oh, question?
Oh, I'm sorry to interrupt you so soon, but I was just wondering if you could just tell us how big of a discovery was this in 1958? Was it a major deal at the time?
This was a major deal. It's put Van Allen on the cover of Time magazine, and this spurred was part of the reason that spurred the U.S. space program, NASA's program, because we suddenly realized space wasn't empty. There was a lot going on there, and not only that, the things that were going on there were hazardous. They could disrupt our communication spacecraft. They could disrupt our weather spacecraft, things that we rely on every day. These spacecraft fly in the radiation belts.
Right, right. And yet these belts have not been fully explored, apparently, right?
That's right. A series of spacecraft have been there, but they haven't been fully instrumented. There's never been 2 identical spacecraft there at the same time capable of making the multi-point measurements that we need to have to understand what's going on. So we've had a fragmentary knowledge. We've had to put pieces together. We've had to make guesses. We've had to make assumptions. But now, for the first time, we've got 2 identical, fully equipped spacecraft going in and out through the radiation belt several times per day to give us the picture we really need to understand what's going on.
Right. And now I think this is a good time to bring Shri into the conversation here and tell us about this discovery. What fascinated me about this discovery is how serendipitous it was. You know, the annals of science are just filled with serendipitous discoveries. But you guys, you launched these probes last August, and you decided to turn on your radiation detector about a month ahead of time. Is that right?
That's right. You know, there was another spacecraft called SAMPEX, which was orbiting in low Earth, and it was just about to re-enter the atmosphere, and we wanted to have an overlap so that we could enhance the science return from Van Allen probes. So we decided to turn on our instrument REPT, for relativistic electron proton telescope, which measures high energy electrons, a whole month ahead of what we had planned, just in order to overlap with the SAMPEX spacecraft. And to our surprise, we found this third radiation belt, and we were completely taken aback by it. We were not expecting it at all. And in the beginning, we thought, oh, maybe there is a mistake in our instrument. Maybe something is wrong with it. And as days went by, we became more and more certain that indeed it was nothing wrong with our instrument. Nature was giving us a spectacular show. So it was a very serendipitous one. Yes.
Right. I guess somebody famous once said that, you know, scientific discoveries often start not with eureka, but with, hey, that's funny. And I guess you had one of those, hey, that's funny moments, right?
Absolutely. I mean, you know, we thought, wow, this looks strange. This looks weird. This looks bizarre. It can't really possibly be true. But then, you know, as we looked more and more at our data, we realized, yes, it's true. Oh boy, this is something really new. It was very exciting for us.
And this third band of radiation, it was temporary, right? Tell me about you know, how you followed it and how long it lasted.
So the third band, or the storage ring, or the radiation belt, lasted for about 4 weeks, I believe. It started off from a prior electron energization event, which we call when the electron fluxes increase.
And that comes from the sun, right? That's a solar event.
Yes, the solar event actually produces changes inside the magnetosphere, which make these belts get pumped up. So when these belts get pumped up, the number of particles in it get energized. They also increase in sheer number. So this is the radiation hazard that David was referring to just a while ago. And when this event happened, after this event, then there was another event which emptied the outer belt, but it obviously didn't empty the whole outer belt. There was an inner sliver of the outer belt left. However, then the energization occurred and the second belt came back on. And at this point, it should have at all become like one single entity. It did not. The sliver continued to last. So we had a 3 radiation belt structure lasting for more than a month.
Right, right. And David, can you maybe explain a little bit why this was so unexpected to see this happen? Are you a good person to explain that?
I can give it a go. We try to model the Earth's radiation belts. We use our most complex computer simulations to know what's going on, and no computer simulation, no model, has ever predicted 3 radiation belts. 2, yes. 3, no. And a third one that comes and goes, isn't there, is there, things get swept up, things come back on these timescales in this way, never happened before. So we have something fundamental here that we need to try to understand.
So the physicist, the plasma physicist and heliophysicist have to go back to work to try to figure out the physics of this phenomenon, right?
Back to the drawing board.
Right. Well, Alex, maybe you can broaden out this conversation a little bit to talk about how, you know, space weather is this term for, you know, what's happening with the sun, the energetic particles that are being shot out into space. And I guess the Van Allen belts are kind of a reflection of the immediate space weather environment around Earth. Could you explain that a little bit?
Well, yes. So there is this constant stream of energy coming away from the sun in the form of particles we call the solar wind. But then occasionally, the sun spits out something in addition. We call it a coronal mass ejection. It's just a big blob of solar plasma that's threaded with magnetic field. And this thing comes along and rides on the solar wind, almost like a surfer, and adds this extra punch. And all of this stuff comes along, and if it's directed towards Earth, it hits our magnetosphere, and all of this energy and all these particles interact with it, and this is an incredibly dynamic system. And so one of the things that's the most exciting about the radiation belts is this is a result of this dynamic phenomena of this injection of stuff, of energy into our local environment. And the problem we've always had in science is the dynamics is always the difficult thing to understand. It's always the thing that's hardest to model. And this is an example where we have this incredibly dynamic transient structure, and it's giving us a direct look at the complex physics that's going on,
right,
and showing us the kinds of things that we really have to be able to understand. Because this whole system, the space weather system, is connected from the surface, well, actually from the inside of the sun out to the surface, all the way through the interplanetary medium to the Earth. So and this happens through the entire solar system. So
right.
we're living inside the atmosphere of a star. The entire solar system is inside this atmosphere.
We're inside the bubble all the time.
Exactly.
And so the inner Van Allen ring is pretty stable. That's what Sri told me yesterday when I interviewed him. But this outer ring is this kind of roiling, dynamic, changing structure, right? It's Sri, could you explain that a little bit? It's constantly expanding and contracting, that kind of thing.
Yes, the outer belt is made up mainly of particles, very light particles called electrons, which wax and wane in response to the solar inputs that Alex was just talking about, coronal mass ejections. There are other things called high-speed streams. When they impact the magnetosphere, they compress the magnetosphere, they create plasma waves, they create other kinds of disturbances, and they will actually act on the existing electron populations to pump them up, to deplete them, sometimes no change, which is what makes prediction and understanding of these populations very difficult, because there are multiple processes going on, processes that will increase the number of electrons, which we call energization, processes that will deplete the radiation belts, which we call loss processes. And these two processes compete with each other to result in the net amount of electrons we see. So if there is more energization, if more particles are energized, then you see an increased number of particles, i.e. particle intensity goes up. If the loss is dominant, then particle intensity goes down. And the trick is, the challenge is to figure out what happens in a particular event and to what extent.
Right, right. And I think Sasha has been waiting patiently here, and I think he can show us a little bit about a visualization of the three rings. Is that right? Do you have an image you can show us?
That is possible. I can try and share it. Let me know if it works. Just 1 second. Screen share, and I hit the movie, and can you see it?
Well, I'm not sure if we can, but maybe you can at least describe the visualization techniques, how you take the data. I can see it in the thumbnails. I don't know if the audience can see it. But,
Oh, I see. So that is too bad. So even if I speak, there is no visual accompanying.
Sasha, try the screen share while you're talking. It should. I would think.
Okay,
I think Carl has.
Yes, let me
and
try
Carl
it
is
one
opening
more
it
time
up.
to test the technology.
And also, Carl has turned it on the thumbnail. Anyone who's watching can click on that thumbnail in the bottom, and it will open up for
Yep.
everyone to view. And while Sasha's looking through the screen share on his, let me remind everybody that anyone who's just joined us recently, we're talking today about the Van Allen probes and the recent discovery of a third radiation belt. We will be taking questions over the course of the hour. We'll be answering them a little bit later. You may send your questions either via the Google Hangout or using the Twitter hashtag Van Allen, which is VANALLEN. Thanks, and I'll hand it back to Sasha and Brian.
All right. Okay. So I'm hitting screen share again.
There we go. Now we can see it.
Oh, that's just great. So basically, before I hit the play button, let me talk, what we're looking at. Obviously, there is a star background, but these white lines that we're looking at, this is a schematic representation of the magnetic field that actually controls the behavior of these high energy particles that the radiation belts are consist of. And you can see this stable inner belt, which will not maybe be as stable during this simulation or animation that I'm showing for reasons that I can go into. But more importantly, you are looking at the slot region and this second belt, which actually is not the full second belt, but the storage ring that you guys introduced earlier. And this animation starts, and I'm going to hit the play button right after one of these systems from the sun came and destroyed the outer portion of the outer belt and just left the storage ring sitting there.
And storage ring is, we should tell people, is lingo for the third belt, right?
That is correct. And the color in this animation basically represents the intensity of radiation in the belt. The brighter the color, the more red the colors are, it means that the more intense radiation levels are in this specific place in the belt.
Now, is this animation showing actual data from the probes from last September?
Basically, that is correct. So basically, under the hood of this animation, what we have is very sophisticated test particle physical model, simulation model of dynamics of radiation belt particles that we've been developing at APL for a long time. But it's driven, what is more important, it's driven by real data coming from Van Allen probes.
Right.
And that's why it accurately shows us the spatial and temporal variations of radiation across the belt.
Right. So what we're seeing here is basically a cutaway view of two toroids or two donuts that go all the way around the Earth, right? This is like a sliced view of that.
Yes, that is correct. So on your left, this is where the sun is, and the opposite direction from the sun is to the right, and you're looking at this two-dimensional cut, the plane that cuts radiation belts in half. And you can see this, like you saw, let me run the animation again, that these white lines that represent the magnetic field, they kind of vibrate, and this is because they directly respond to activity that is driven by the sun, and this is why you have difference on the left-hand side and right-hand side, and this is what is affecting the dynamics of these particles that are forming radiation belts.
Right. Well, thank you for showing us that. It's very cool animation, and I think it helps people obviously visualize what's going on. David, can you tell us a little bit about, or maybe this is a question for Alex. You mentioned satellites being affected by these radiation belts. I mean, how serious of a threat are they to communication and weather satellites? Do they have to, turn off instruments when they fly through these belts? Do they have to take other countermeasures to protect themselves?
That's certainly a possibility. The principal thing is they should be designed with thick enough shielding to protect the electronics within the instruments. But the thicker the shielding, the greater the mass of the spacecraft, the heavier it is, and the more it takes to launch it into space. So we'd like to know what's the minimum requirement that will cut costs for spacecraft. Then second, these effects are sufficient to knock out an entire spacecraft and ruin it. So we have to have the knowledge of when and where these type of events will occur. And third, as you just said, there are some spacecraft that carry instruments so sensitive that they would be ruined by these effects, and those instruments have to turn off during a storm like this.
Right, right. Alex, has there been a case, or let me ask all of you, has there ever been a case of a satellite being damaged or rendered inoperable by the radiation belts?
Well, I mean, it's certainly the case that satellites have been damaged and critically damaged by energetic electrons.
Right.
Let me jump in for a minute. We expect that will be the ultimate fate of these Van Allen probe spacecraft. Prolonged exposure to the radiation belts will one day kill them. They're in the most hazardous possible place.
Do you have any
idea? To answer
how...
your question, Brian, yes, I can. I certainly remember one instance which affected society fairly moderately, I would say. This was a loss of a Canadian communications satellite called ANIK, A-N-I-K, and I believe the Canadian newspapers carried a headline by putting a P in front of it, saying panic. So it knocked off communications. I cannot recall on the top of my head when exactly it was, but I'm sure all the readers, viewers on Google can immediately Google ANIK and they'll find out.
Right.
Although the thing is, it's difficult to associate, to pinpoint the exact cause, but the satellite died just when electron fluxes were very high. So it's extremely likely that they would cause the failure.
So it's suspicious, right? And so that, of course, brings us back to the point that being able to predict the behavior of these belts is very important for commerce here on Earth, and I guess for astronauts too, although the outer belt is beyond low Earth orbit. But what are the risks to space travelers? Who wants to answer that question?
I can take a crack at it. If you are doing any interplanetary travel, let's say, for example, you want to go to Mars, so you would have to go through the radiation belts, I mean the outer radiation belt. When you're doing that, if in case of manned flight, it's fine if you're inside the spacecraft, which is well shielded. But if you're outside the spacecraft, and for whatever purpose to do a EVA, then you can be in serious danger, because the only thing that separates you from space and the radiation in it is a thin spacesuit.
Right.
In addition to that, one has to wonder about the collective dose that accumulates as one travels through the radiation belt. So in principle, there could be a hazard.
Right. So you would want to time your space mission for when the belts are quiet, right?
Exactly. If you can do that, that's, from the science point of view, if we can understand the science enough to be able to predict when the most severe events will occur, how long they will last, and that will enable a safe passage for these astronauts.
Right. Alex, it looked like you wanted to jump in there.
Yeah, I just wanted to add something to what Sri said. When we're talking about energetic particles, electrons, protons, that space travelers are exposed to, it really is the main concern is this long-term dose. Astronauts have an allowed amount of radiation, accumulated radiation, over their time as an astronaut, and if an astronaut reaches that limit, then that will be permanently grounded. Right. So it is really critical to understand this long-term dosage. That's of utmost importance.
Right. I think Karen has some questions for us.
I do. I just want to remind everyone that we are taking questions over the course until 2 o'clock. You can send them via Google Hangout, via the Twitter hashtag Van Allen, and we'll start throwing some of them out now. First one we're going with is from @Nicopotamus. The question is, what are the conditions that influence when the third Van Allen belt is measurable, and how is it that it has never been noticed before? I'm going to throw that question to Sasha for starters, and if other people want to jump in, they may do so too.
That is a very good question, and I mean, if we knew all the conditions, probably we didn't need to fly Van Allen probes at all, because then we would have known all the answers. So this is basically up for the discussion in science papers and science analysis that we're running. The reason is that we didn't have this, really comprehensive capability of basically producing radial cuts that you saw in the visualization that appeared on my screen, and getting these almost instantaneous snapshots of radiation intensity and its variability across the entire system. Now, actually, after it was discovered, we found several other data sets where we see indications of similar structures, but this will be definitely up for in-depth science analysis and discussion, because as Sri and David mentioned multiple times, there is a whole complexity and multitude of various acceleration and loss processes that can create this really complex profile and variable profile of radiation intensities across the belt.
Great. I will add on another question here. You'll notice down in your thumbnails there's a big image of a sun. If anyone who's watching wants to click on that, it'll show up. You can see it nice and large in the middle of your screen. That is an image of a prominence that occurred almost at the same time as the launch of the Van Allen probes. We have a question from David Saul, who is wondering about that prominence. He's asking how long it is, and probably other information about what happened to what it sent out. And I'm going to throw that question to Alex Young, because I know he has watched this prominence and commented on it before.
Yes. So what you're looking at, and the structure is a little bit hard to measure. First, because we're looking at it in a two-dimensional image and we're looking at it at an angle, but just doing a rough estimate, it's at least 30 plus Earths side by side in length. So hundreds of thousands of miles, up to hundreds of thousands of miles. So this is an incredibly huge structure, and the Earth itself would be completely dwarfed by this. And what happens is we have this material on the surface of the sun. It's relatively cool compared to the surrounding atmosphere. This is material from lower down in the solar atmosphere that sits up much higher in what we call the corona, the outer atmosphere, and it's supported by magnetic fields. We don't exactly understand the full mechanism, but in some ways you could sort of think of it like a long skinny balloon that's been held down by lots of strings, and that's the magnetic field. And occasionally those magnetic fields become unstable. When they do that, they basically pop. They release energy in something we call, plasma physicists call magnetic reconnection, and that accelerates this big piece of solar material out into space at millions of miles an hour, and once it leaves the sun and enters space, we call it a coronal mass ejection. And so this is the material that eventually becomes that giant blob I was talking about that will travel and sometimes slams into the Earth's magnetic field, or the Earth's magnetic system, called the magnetosphere.
Right, and actually inject energy into the outer ring. Is that right?
Exactly. Well, you remember you saw the video that Sasha was showing with the magnetic fields kind of wiggling. When this coronal mass ejection slams into the magnetosphere, it's almost like hitting a bell. It causes it to ring. The magnetic fields move back and forth and oscillate, and that's putting energy in the system. And one of the things that's doing, it's actually generating electrical currents. If you take a magnetic field and change it quickly, it generates a current. And those currents build up in the upper atmosphere and can eventually be induced and can eventually induce currents on the ground. And that's of huge concern because it can affect power grids, long pipelines. So that's one of the major impacts of space weather that we're very concerned about.
Great, thanks. Do you have another question, Karen? Or
Absolutely. I wouldn't mind doing a quick follow-up on that. Then I will go to the next question. But Shri, do you think you could comment quickly about that particular prominence and the CME, since this obviously happened right when the launch happened? It didn't necessarily cause the influx of energy that was the solar storm you launched into, but it may have had some effect causing the interplanetary shock that initiated that third radiation belt. Maybe you can comment on that, whether or not they were connected, or what you're thinking if they were connected.
Yeah, it's hard to say, whether this particular one caused it, but in general, when there is a interplanetary shock or a coronal mass ejection, what often happens is that we see a loss of particles, which we call a dropout, and then they emerge again, sometimes stronger, sometimes more intense, sometimes anemic, sometimes to the same level. In this case, the event that caused the dropout and the subsequent energization resulted in this third belt, and that is the puzzle we are trying to understand, why it did not behave, why the magnetosphere did not behave the way it usually does. And this is also in response to the earlier question. This is a clear case where I believe observation leads theory or models. Observation suddenly thrown out a challenge. We have seen something in nature, and now it's up to modelers like Sasha, who can theorize and give us a physical explanation as to what's going on. And so the observation is really, in this case, leading the whole scene.
All right. Let me bring in question from Tommy Henley, who sent in a question via Facebook. And he's asking about the instruments on the probes, what they measure. He asked, did the instruments measure the intensity of the energy field? And wants to know what they saw in the second radiation belt. Did the second radiation belt attain a fairly constant and maximum intensity during the existence of the third radiation belt? And I would love to hear both from David about the instruments specifically on the Van Allen probes, what they measure, and then Sasha, maybe you can tell us what was seen in the second radiation belt.
Okay, I think that's a good division of labor. The instruments on the Van Allen probes measure the magnetic fields that confine and trap these dangerous radiation particles in Earth's near environment. They measure the electric fields that can give energy to the particles out in space, and they measure the full range of particles from the lowest possible energies up to many millions of degrees of temperature or energy. They measure the composition of the particles, protons, helium, oxygen. All these observations are needed to give us the clues about how particles are energized from the relatively cold energies that the Earth's ionosphere provides, or a bit warmer from the solar wind, up to these dangerous energies. And with that, I'll pass it to Sasha.
What I would like to also add to David's description is that we perhaps should be very clear that by radiation in this specific context of radiation belts, we mean very, very high energy particles that can produce damaging effects to technology or to astronauts, as we already have been discussing. But the goal of our mission is not just measure these intensities, the intensities of these particles, basically how many at what energies these particles are, but really understand what governs the basically increases or decreases in these intensities. And this is why we need to measure, as David just pointed out, all possible energies and all wave, magnetic or electric fields that can contribute to both production and losses of this radiation across the entire inner magnetospheric system. And it was a very good question, because it kind of led us to mentioning again that the innermost part of the magnetosphere, which is the inner belt region, is generally stable. Usually, and it's important to understand that sometimes we do have very dramatic effects that affect the entire system. But usually the magnetic and electric fields in the inner belt are more or less quiet. So that's why the inner belt system is more or less stable. And this is exactly what was shown by these measurements, that while the outer belt dynamics was really dynamic and rapid and different at different radial distances, the inner belt was very, very quiet.
I think Alex is going to add on something to that too.
Yeah, I just wanted to mention that one of the areas that we're very interested in is trying to predict the whole chain of events when the coronal mass ejection impacts the magnetosphere, and understanding exactly what is the impact, for example, on the ground. And this inner area between the upper atmosphere, going from the upper atmosphere through into the magnetosphere, this whole region is one of the hardest ones to understand, or ones we don't understand very well. So this is just one more piece of this puzzle of connecting these different parts of the whole system. And it's giving us an incredibly new dynamic look at this whole process.
Great. Another question in from @virtuallinda, who is asking us, do the Van Allen belts change when there is a CME from the sun? We talked about this a little bit, but we have a couple of questions on this. I want to go over it again, that as well as a question of what are the conditions in general that influence bringing on the third radiation belt, and is it just that it's too small to see normally, or what's making it pump up into being something visible? Why don't I start with Shri on that one?
Okay, yes, in general, coronal mass ejections, disturbances from the sun, which are headed towards the Earth and impact the magnetosphere, have results in some dynamical change in the radiation belt system. Most of the time, the change is affected only in the outer radiation belt, but sometimes the disturbance and the impact is so strong that it will create a whole slew of particles which will move inwards and even join the innermost belt, the proton, the generally stable proton belt. As to what caused the third radiation belt, I've already mentioned. We are trying to understand theoretically why the belt stayed stable, why it did not just mix up and become just back to two belts. That we have to understand. However, the dynamical changes that are caused by these solar drivers, the plasma blobs, the coronal mass ejections, they result in a very complex response by the magnetosphere. As I mentioned, sometimes the intensities increase, and the increase is often orders of magnitude, like 10,000 times the original level of electrons. Sometimes they don't change at all. Sometimes they actually get wiped away. And why these things happen in a given particular event is the subject of scientific inquiry. I hope that answers the question.
I think so. We have a question from @MBC Cohen. He's asking, what percentage of the protection to Earth comes from the new third belt compared to the other two? Now, my understanding is, of course, that the radiation belts are not offering us protection, or maybe they are. Are the radiation belts offering us protection from incoming events on the sun? And if it's not the radiation belts that are doing it, what is? Why don't I send that to Alex, please?
Actually, I think that's probably that Dave should answer. David should answer that.
Okay. Well, the radiation belts are confined in the immediate vicinity of the Earth by the Earth's magnetic field. They're not shielding us from anything. They're trapped and circling around the Earth in these donut-shaped regions, and they're posing a hazard to us. They don't protect us from anything further out. They're trapped by the Earth's magnetic field. The Earth's magnetic field is a buffer that's trying to shield us from particles further out, but some of those particles get in, get energized, and become the Earth's radiation belts. I think Sasha may have more to say.
Maybe just to add a little bit, it's important to emphasize that the inner magnetospheric system where radiation belts are embedded in acts actually as an accelerator. There are a number of wave or field processes that accelerate particles, and it's not particles that are coming directly from the sun, although of course ultimately the sun is the driver of all the activity that is affecting us, but something else and some other serendipity of activities happen across the inner magnetosphere, which sometimes accelerate particles at very large quantities to very large energies, and this is what basically creates the inner belt and outer belt populations. And we mentioned space weather a number of times, but it's also is important to understand that these high energy particles cannot be created at Earth except in very expensive and very different laboratory conditions. But having observations right inside of the inner magnetosphere where these radiation belts are basically provide us with natural laboratory for understanding how particles are accelerated across the universe, which is really a fundamental question that we physicists are extremely excited about, and these are unprecedented observations that give us hints about that.
Can I ask a follow-up on that? Because that's a very interesting point there. So you're saying that studying these belts complements, this $10 billion Large Hadron Collider we built here on Earth. Is that kind of what you're saying?
It actually, in some sense, yes. In the sense that from both remote observations and direct observations at other outer planets like Saturn and Jupiter, or basically galactic center and other systems, we know that if you have strongly magnetized, and by that I mean systems with magnetic field, it tends to create very high energy particle population, which is basically important to understand for us to understand how the universe works. And we cannot really fly to Andromeda or to the galactic center or even to Jupiter. It's very expensive. But right, here in our backyard, we basically have perfect conditions for just stepping outside and looking how these particles are being produced and how these populations are affected by electric and magnetic waves that basically shape them up, which is an extremely fundamental question. And yeah, ultimately maybe unlocking some mysteries related to elementary particles. I don't know that.
Well, if I may jump in, I would say somewhat differently. I would say the LHC and those sorts of endeavors are somewhat complementary to what we are doing. They probe different energy regimes, they probe different phenomena. But what is interesting to amplify what Sasha said, the energization processes that occur in the radiation belts, in our own backyard, as he put it, occur throughout the universe. And in order to understand, if we understand processes completely, fully here, we would be able to understand these processes occurring in distant parts of the universe. So from that sense, what we do is important.
All right, just a reminder, we have about 15 minutes left, so we're still taking questions until 2 o'clock. You can send them to us via the Goddard Facebook page, you can send them to us via Google Plus Hangout, or via the Twitter hashtag Van Allen, V-A-N-A-A, sorry, V-A-N-A-L-L-E-N. And we have a question from someone via Google Plus. Andrew Planet asks, the planetary magnetic field alters the patterns in charged particles relative to the changing intensities of the energy applied to it. I wonder if it would be easy to replicate the conditions that produces the Van Allen belt in an experiment in a lab on Earth. This would be especially interesting with all the new data. Sort of the flip side to talking about using space as a laboratory, can you recreate that environment on Earth in the lab? And let's, I can throw that out. Who wants to take that one?
I'll start for a minute and then pass it on. It's a great idea. It's an idea that scientists are working on. In fact, it's an idea that they've been working on for many, many years. The earliest Torella experiments involved shooting beams of charged particles at a magnetic field, simulating their Earth's magnetic field, and seeing which way those particles go and how they get trapped. But the difficulty here is the change in scale size. In your lab, you can only have a little small magnetic field, and you can't get all the phenomena on the right scales that happen out in space. So we do conduct lab experiments, put probes into them and measure waves, measure their effect on the particles, and we do our best. And we also conduct simulations where we put in all the factors we believe or should be occurring, and then press the button and let those simulations run and try to predict what will happen. Maybe someone else will comment too.
Well, I wanted to add to that, and I guess kind of back to what Shri and Sasha was talking about, that one of the most exciting things is that we do have a new laboratory. Because plasma processes and particle acceleration processes are ubiquitous throughout the whole universe, we're always looking for different places where we can sample different time scales and spatial scales and temporal scales to really understand all the different aspects of the process. So this is just one more place that we have a laboratory very close to us. And when you think about processes in the universe, one of the things we're trying to really understand on the sun is we know particles are accelerated to create the solar wind. We know particles are accelerated during a solar flare. So we don't understand exactly how they're accelerated. So these particles are what help to create the radiation belts, and we're using the radiation belts now to understand the acceleration processes that then create the solar flares and the solar wind. So the two are incredibly complementary to each other.
All right. Anyone else want to add to anything in the laboratory setting?
I can just quickly add and basically echo what David and Alex said, that while there are some absolutely fantastic efforts in laboratory plasma, the huge issue is scale size. It's almost impossible to take the entire inner magnetosphere and put it, down in one room laboratory environment. And unfortunately, processes and energetics of the system don't easily scale down at that level. So that's why, if we want to really understand what happens in natural astrophysical systems, we really need to, once again, using the same analogy, go to our backyard and fly a little bit out of the atmosphere and start sampling the system there. That's all I want.
I think Sasha really hit the nail on the head here by saying that phenomena do not scale if you in size. So if you just take and try to miniaturize and recreate Van Allen belts on Earth, it's no guarantee that the phenomena that we observe in nature will also be present in the scaled down version. That's the key.
I can't help but wonder if you guys have been talking with these folks who are trying to make magnetic fusion work as an energy source here on Earth. They're trying to create plasmas and magnetically contain them in the lab. Have you talked to any fusion researchers about what you guys are doing?
It's interesting you bring that up, Brian, because I think there are many, there are some aspects which actually apply to both fields. Things like plasma instabilities and so on. Indeed, it's not unusual to see a plasma physicist wandering into the space science arena and vice versa. And I think probably Sasha might actually have more to add to this.
No, I think you've done a good job, Shri, in a sense that, as has been said before, the processes that accelerate particles are ubiquitous, and there are lots of lessons that we can learn from each other. However, there are some very basic differences between the laboratory experiments that target a controlled fusion and the regimes in space plasma, which is kind of a very short version without getting into technical details.
Right. I got off on a tangent there a little bit. My curiosity got to me. But maybe this is a good time to just kind of remind the viewers what this overall mission was all about. I mean, you guys hit the jackpot and made a original discovery on about the third day of the mission. But what was the point of launching these two probes in the first place?
Maybe I'll go for that. It's pretty basic. Where do these energetic particles come from? What causes them to get those energy? What moves them around? And what gets rid of them? We've seen all of these within the first few days of the mission in ways we didn't ever expect to see, but now the point is to figure it out, to understand it, to be able to predict it, to put it to use for humanity in the sense of protecting astronauts and spacecraft. That's the purpose here.
So well said that I can hardly add anything to it.
All right. Just a reminder, we'll get your last few questions in. We'll be ending promptly at 2. So send your questions via Google Hangout or the Twitter hashtag Van Allen. And once we're finished, this will be up on YouTube for all time. So you can keep watching it over and over and over again if you wish. I'm going to throw in a question here, which is, we're talking about the effects of the radiation belts, the discovery of the radiation belt, just as sort of it's a cool discovery, and what can that mean for space weather. I'd like to go a little deeper into what does that mean for modeling and predicting. What exactly does seeing this extra belt, or for that matter, you can think of it as seeing an extra space, right, an extra slot region between the belts. What does having that slot region mean for the next steps of coming up with theories? And why don't I throw that to David?
Well, we have to go back to Stretch and ask, why do these gaps appear? Where do the particles go, and where do they come from? It's not that we have a shortage of theories. In fact, we have a surplus of theories. In fact, as many scientists as there are theories. And that's what makes going to a science meeting so interesting, because you see them arguing about them, saying, no, my theory is the right one. But the way we're going to test them, all of them have plausible ideas, is turn to people like Sasha and ask him, can you put this in a model? Can you tell If we tell you it's this strong and this big and happening here, and now run your model and tell us what you see. Do you see what was really observed? If that effect doesn't work, try this effect. Move on to the next one. Maybe it's a combination of 2 or 3 or more. Let's get it right. When Sasha gets the model running right and makes predictions for us, then that's the model we want to run to make real space weather forecasts. Sasha, some comment?
Maybe a very quick one, because once again, I think that your short answer kind of encompasses it. But going back to Brian's question, this is exactly why we cannot end the mission now. We had this, cool discovery of this really interesting and dynamic structure, but going kind of to the reason for the press conference and the science paper is that structure perhaps has never been observed before. So it just points us to, again, the fact that we're dealing with very, very dynamic system, and we really need comprehensive measurements to use for these, models and theories that David just mentioned before we can really constrain them or make, more questions and get more puzzled for future space missions and future experiments and discoveries.
Great. We have what is probably going to be our last question. Just came in from Facebook from Heidi Can. The question is, what moved you to use the instruments almost immediately after launch rather than later? Why don't I start with Shri on that one?
Okay, so as I mentioned, we, on the REPT instrument, which observed these new radiation belts, many of us were also part of an older satellite mission called SAMPEX. Now, SAMPEX was the very first so-called small explorers. It was launched in '92, and it was expected to last merely 3 years. However, it lasted 20 years, and it was just about to come down late November last year, just few months after RB or the Van Allen probes were launched. So we wanted to increase our scientific return by making simultaneous measurements, while SAMPEX was what we call in a low Earth orbit. It was at close to the Earth's surface, and Van Allen probes are in an equatorial orbit, which is at a very high altitude, goes all the way to 6 times Earth radii. So we decided to turn our instrument on day 3 instead of day 30, hoping to get some new science by conjunction studies, as we call them, with this other low-flying satellite. And by the way, we are still exploring that option. We are analyzing the final data collected by SAMPEX. So that was the reason why we turned on. And then, as it happened, we got lucky. And the sun was most benevolent to us and provided us with this event, which turned out to be a completely unexpected but a very exciting surprise.
Well, we are just about up with our hour today. I want to thank everyone for being here. Thanks everyone for watching, and thank you to all the people who participated. Brian Vastag from the Washington Post, Alex Young, and Dave Sybeck and Shri Kanikal from Goddard, from NASA Goddard, and Sasha from Johns Hopkins APL. It's been a great discussion. This will live on YouTube afterwards, so if you enjoyed watching us today, feel free to send the link to all of your friends. And of course, you can watch it again and again. As well, for more information in the future on heliophysics research at NASA, you may go to nasa.gov/sun-earth. That's one word, sun-earth. And a reminder that YouTube link will be available at YouTube/NASA Explorer. One word. We've had a great time with you all today. Thanks for sharing in a new media attempt with us. Thanks for scientists for trying it out with us too. And goodbye.
Bye-bye.